Hello everyone. Welcome to YouTube channel Energy-Exergy Theory Applications. I am Morosuk and I am author of this channel. Today we are with the lectures on engineering thermodynamics. All lectures have a very dynamic style of presentation. Definitely some of you would like to learn more. We will be happy to answer your questions and provide with extended information. Please find our contact email in the description of this video. Lecture 6, it is still continuation of the second law of thermodynamics. And today we will discuss the Carnot theorem and Carnot corollaries. Maybe you know this, everything that we will discuss today, maybe you know under different names. It can be the case that in thermodynamics books in different languages, different titles are used for this concept within the second law of thermodynamics. So, what means Carnot theorem? It is the definition of maximum theoretical efficiency of thermodynamic cycles. Does not matter if it is direct cycle or it is inverse cycle. For us, it's the most important to find maximum theoretical efficiency. It is called Carnot theorem not because Carnot developed these equations and the principles to say maximum theoretical efficiency. Everything is dedicated to the name of Carnot, of his contribution to thermodynamics. So let us continue with the evaluation of three energy conversion systems, or three thermodynamic cycles, better to say. One is heat engine, it is a direct thermodynamic cycles, and two inverse thermodynamic cycles, it is refrigeration machine and heat pump. So we know that maximum theoretical efficiency, as you can see here, is even written performance. This word also will be correct to use, can be achieved if energy conversion system will operate according to the Carnot cycle. So again, Carnot did not propose cycle. The cycle is dedicated to the Carnot to appreciate his contribution to thermodynamics. So we have here three thermodynamic schematics of energy conversion systems. I repeat: heat engine, refrigeration machine, and heat pump. And here below, we have already three Carnot cycles and thermodynamic TS diagram. TS diagram, it is basic equation of Clausius when he introduced the concept of entropy, and this is rectangles. When thermal energy is supplied to the system, definitely we have change in entropy. When thermal energy is removed from the system, rejected from the system, we have change in entropy. And two other processes associated with work, theoretical work, and we know if theoretical work is crossing the system boundary, entropy stayed constant. Therefore, in TS diagram, Carnot cycle, it is rectangle. And maximum efficiency for the energetic efficiency for the heat engine, it is maximum possible work produced within the cycle divided by so-called driving energy, which is heat at higher temperature level. And here in red color, I mentioned that this value will be constant. And if we have any irreversibilities within the system, this will affect to decreasing of work produced by the system. At present, work is maximum, efficiency is maximum. Similar discussions we can apply for the refrigeration machine and for the heat pump. For refrigeration machine, the positive effect, it is refrigeration capacity. Therefore, this value will be constant, and minimum work that is supplied for refrigeration machine will correspond to maximum efficiency, coefficient of performance. The same for heat pump. So now we have the difference that for power cycles, for direct cycles, we will produce maximum power, but for inverse cycles, we will supply minimum power or minimum work to achieve positive effect. Then COP, coefficient of performance, for refrigeration machine and for heat pump will be maximum possible. Now we will discuss more detailed application of Carnot theorem for heat engine, and third, a little bit later, for refrigeration machine and for heat pump. We know this equation, that maximum efficiency, it is maximum work divided by driving energy, and immediately we have mathematical expression where only temperature of both sources is used. So from the heat and work transfer, we move it to temperature. So now we need to discuss all this step-by-step analysis to proceed from one equation to another equation. So this is a Carnot cycle in TS diagram. We already discussed it before. And we have equation. So this equation now, each step will be more discussed in detail. So work of the cycle, work produced by cycle, it is work of the cycle. We discussed this earlier. We can rewrite as Q hot minus Q0. So means heat supplied at high temperature level minus heat rejected to the lower level, environmental level. This is absolute correct from thermodynamic point of view. And using the Clausius equation, heat we can rewrite as temperature and the difference in entropy. Next figure and immediately graphical interpretation. What is it? Heat in TS diagram. It is area. And immediately equation how to calculate this area. It is the change in entropy multiplied to temperature at higher temperature when heat is supplied to the system. This we need always to remember that work and heat in TS diagram, it is always area. And we will use later thermodynamic analysis cycles in TS diagram. Always we will discuss with areas. So you always should keep in mind that heat and work, it is area in this diagram, not in all diagrams. Next step, heat rejected to the environment, Q0. It is area under the process with lower temperature level. Finally, delta S, change in entropy for heat supply and heat reject, it is the same. Delta S disappeared from the equation, and we came to the initial our equation when maximum efficiency depends only on temperature of two thermal reservoirs. And the difference between Q hot and Q0, it is work of the cycle, it is area of the cycle. So now we're with a similar analysis for refrigeration machine. Again, COP of refrigeration machine, we have equation that it is refrigeration capacity over minimum work supplied for the cycle, and we will end with the temperature of heat sources. So first it is thermodynamic cycle, Carnot cycle in TS diagram. Second figure, refrigeration capacity, it is area below the process where we will generate refrigeration capacity, our positive effect for the refrigeration machine. Another area, it is heat rejected to the environment. Energy in minus energy out, as we can see, it is negative because we will supply less that we will reject, means that work should be supplied. So this is principle of refrigeration machine in their thermodynamic cycle. Delta S of the cycle and area of the Carnot cycle, it is minimum amount of work that required for the operation of refrigeration machine. And let us repeat third time this analysis, but now for a heat pump. First, it is thermodynamic cycle, Carnot cycle in TS diagram for the heat pump. Area that heat we're taking from the environment at lower temperature level, because for heat pump we would like to leave the heat from the lower temperature level, means environmental level, to higher temperature level. This is area. Another area, it is heat that our positive effect of the system at higher temperature level. Delta entropy of the cycle, and area of the cycle, it is minimum work that we need for a heat pump. For the work of heat pump, and as before for refrigeration machine, heat in is lower than heat out, therefore work should be supplied for the realization of inverted thermodynamic cycle. So Carnot corollary 1. According to this corollary, we know that if we have irreversibilities within cycle, direct or inverse, any of irreversibilities immediately will cause the decrease in efficiency. So it means that for a direct cycle, for power generation cycle, we will produce less work than maximum, but for refrigeration machine and for heat pump, we need to supply work more than minimum. And now you can see we have already complex this description of energy conversion system, of a thermodynamic system. Already we have some blocks closer to thermal reservoirs. So let us proceed with discussions what means these blocks. And as usual, we will start with the heat engine. Now we should remember the definition of system. So system, it is our subject of analysis. For this slide, it is heat engine, and everything which is not included to the system, call it surroundings. We already discussed that. So to divide system from the surrounding, we need to introduce system boundary, and also we know other concept that can be also associated with surroundings. It is oven closet systems, which are called thermal reservoirs. I hope you remember that definition, because already in previous slides we used thermal reservoirs. So what is the idea of heat engine? Heat from a thermal reservoir with higher temperature level will be transferred to the system. And this part of this heat will be converted to the work, and another part will be rejected to the thermal reservoir with lower temperature level. We are engineers. We understand that it is thermodynamic concept of two reservoirs. From reservoir to system, only heat can be transferred, but not working fluid. But energy conversion system cannot operate without working fluid, because heat always transferred with the conveyor, and working fluid is the conveyor of heat. Therefore, we have in real life the following situation. So in real life, in real thermodynamic life. So let us assume that still we have heat reservoir with high temperature level and low temperature level. So, but system consists of oven reservoir with higher temperature level, with lower temperature level, and all processes within the system. So, in this moment already we have working fluid of the system. So we always should have delta T heat transfer from the reservoir to the working fluid of the system, from the working fluid of the system to another thermal reservoir. And now you can see that we will not produce work between T hot and T0. We will produce work between the higher temperature level within heat engine and lower temperature level in heat engine. Therefore, the work produced will be definitely lower, and correspondingly efficiency will be lower. Carnot corollary 1, it is also Gouy-Stodola theorem. Again, not in all books, in all languages, use the term Gouy-Stodola theorem, also use another term that I will mention a little bit later, but everything, this is synonyms term, and if not this term used, it doesn't mean that you missed something in your study. Okay, what means Gouy-Stodola theorem? That real heat engine will generate less work than maximum theoretical possible, and the difference it is delta W. So it means that we will miss this part of work, and since we will miss this part of work, efficiency will be lower. But now the question: how to calculate this part of work? This part of work, it is entropy generation within entire system, and according to this equation, temperature of the environment. Exactly, this equation is well known as Gouy-Stodola theorem, as I already told you, but also well known as lost work theorem. So we will lose work, and amount of this work is described by lost work theorem. It's very interesting that this equation, two researchers, they obtained this equation completely independently. The work of Gouy was written in French language in 1898, and the work of Stodola in German language in 1904. Of course, in that period of time, 6 years, it was not very long period of time, no internet, no international journals where research published, and time of transfer of information, of course, was very long. But important that both researchers got absolutely the same equation. But what is interesting to mention, in both languages, in French language and in German language, written absolutely the same, that amount of work that we will lose because of irreversibilities, it is entropy generation within the system. Yeah, but T0 is described as the lower temperature of the system, of thermodynamic cycle. So, but since both researchers discussed heat engine, definitely that the lowest temperature of the cycle, it is environmental temperature. But if we will have some cycle where the lowest temperature is not environmental temperature, this should be in general discussed. But now it is the common term that delta W as work lost, it is entropy generation and temperature of the environment. This is very important to remember. There are some differences between classical work, I mean original work, and modern interpretation. So now we are with Carnot corollary for refrigeration machine and for heat pump. I will do it simultaneously because both are inverse thermodynamic cycles. So we have ideal refrigeration machine with refrigeration capacity and minimum work supplied for the refrigeration machine. What means T cold? Now it's very interesting to discuss with us what it means. It is, of course, thermal reservoir, but from our other point of view, it is the product that should be stored. Heat pump, high temperature level of heat reservoir where heat should be transferred, so lifted from environmental conditions to higher temperature level. What means this higher temperature level? It is heating system for us. So what do we need from refrigeration machine and from heat pump? Now dynamics will be absolutely the same, just with different temperature levels. Heat from our product should come to the working fluid of refrigeration machine. Now we have lower temperature level for refrigeration machine. This heat should be transferred to the temperature level higher than environment, and work should be supplied. And after that, according to the second law of thermodynamics, always Clausius statement that heat is transferred always from hotter reservoir to colder, from hotter to colder. So I repeat, if we would like to cool down the product, we should have thermal reservoir with temperature lower than the product, that heat will come itself. After that, using refrigeration machine will be lifted to the temperature higher than environment, and after that, remove it to the environment. Definitely, the work that we need to supply now from even lower to even higher temperature level will be higher, and efficiency, definitely COP will be lower. Absolutely the same we can discuss for the heat pump. If we would like to take the temperature heat from the environment, it means that we should have another thermal reservoir with temperature lower than environmental temperature, and heat from the environment will come itself to the heat pump. After that, heat pump will lift heat to the higher temperature than we need for the heating system, and after that heat will be supplied to the level of heating system, because this is the main goal of heat pump. Definitely work that should be supplied for heat pump will be higher. And now we have COP with already including these irreversibilities for refrigeration machine and for heat pump. So for refrigeration machine we have more power keeping the same refrigeration capacity. For heat pump we need more power keeping the same heat as a positive effect for the heating system. And now, few words regarding the thermodynamic theories and also regarding the terminology. As I already mentioned, Gouy and Stodola independently say that extra work that we need that we cannot generate for the heat engine, it is entropy generation and the lowest temperature of the cycle. This equation we can use like a copy paste for the heat pump. So work for the heat pump, it will be minimum plus extra work that it is entropy generation and lower temperature of the cycle. But for refrigeration machine, it's very interesting because T0, it is not lower temperature of the cycle, it is higher temperature of the cycle. And all thermodynamic analysis and also prove the Carnot corollary regarding the refrigeration machine, it was already done much later in 50s in Refrigeration Institute in Odessa, and now it is absolute clear statement that always work that we cannot produce for heat engine because of irreversibilities, or extra work that we need extra supply for refrigeration machine and heat pumps because of irreversibilities, it is entropy generation of the cycle and temperature of the environment, regardless which cycle we will discuss, heat engine, refrigeration machine, or heat pump. And now one more topic that we already need to introduce in our discussions. I already mentioned that heat from the thermal reservoir cannot be transferred to the heat engine, refrigeration machine, heat pump, does not matter, should be transferred to working fluid. So from this moment, we always should discuss not only energy, transport, how energy should be transferred within the energy conversion system, heat engine, refrigeration machine of heat pump, but also we need to include the topic of working substance or working fluid. So now we will continuously discuss so-called thermal design, always conjunction with energy and working fluids, because working fluids also can affect to the performance of the cycles. And now in graphical interpretation, everything that we discussed before. Here we have performance, general term, because simultaneously we have energy efficiency and also COP for refrigeration machine and for heat pump, and possible areas. This is very interesting horizontal scale. It is relative scale. Temperature divided by temperature of the environment. So when we have 1, it means that it is temperature of the environment. And all these border lines for refrigeration machine, for heat pump, and for heat engine, this is maximum possible efficiency according to the Carnot theorem. And areas, it is practical real value of performance of these energy conversion systems, because depends on which kind of irreversibilities we have and how big are these irreversibilities. Definitely we always will be below of maximum possible value that is described by Carnot efficiency. And Carnot corollary too, very simple, and I will give only example on heat engine, because for refrigeration machine and for heat pump it will be absolute the same. That always efficiency depends only on temperatures of thermal reservoirs and completely independent from the size, so horizontal size of the cycle. Cycle can be very narrow, can be very wide, does not matter, because the value delta S, entropy change of the cycle, vanished from the analysis and it will not pay attention to the efficiency of the cycle. But using this slide, I would like just to pay your attention, because later we will need this information. We already learned that area of the cycle associated with the work. and area under processes associated with heat supply and heat reject from the cycle. Definitely for this cycle, specific work will be lower value. For another cycle, specific work will be higher, but heat supply here will be lower, here will be higher. So absolute values will be different, but efficiency will be the same. This is very important for our coming discussions. And we finished with lecture 6 today. If you found this lecture interesting for you, please give a like to this video, subscribe to the channel, and share the link with your colleagues. Our next lecture, lecture 7, still we will be with the second law of thermodynamics, and we will already discuss thermodynamic cycles. We will discuss ideal cycles and theoretical cycles. Thank you.